Hi, this is Chris, and we are taking a look at questions 16 through 18 in Section 3 of SAT Practice Test 2. So let's go ahead and get started with question 16, which reads, the sales manager of a company awarded a total of $3,000 in bonuses to the most productive salespeople. The bonuses were awarded in amounts of $250 or $750. If at least one $250 bonus and at least one $750 bonus were awarded, what is one possible number of $250 bonuses awarded? Okay, so on a question like this, a lot of times we want to try to create an equation from the information provided in the word problem. And there's a couple ways you could do this. So you could assign different variables. You could say that the $250 bonuses, there's X number of those. And then the $750 bonuses, there's some other number of those. Let's call that Y. And then we could say that when you add up the total value of both bonuses, you would get $3,000 in bonuses. So this is one equation, but it's one equation with two variables. So that means that to solve this, we would need it to be a system of equations. And they don't give us an exacting number for the number of bonuses provided because it just says at least one of each. So then that means that if there's at least one of each, the only thing you could come up with here is an inequality. You could say that if there's at least one of each, so if X has to be 1 or greater and Y has to be 1 or greater, then we know that together there would have to be at least one for each. So it's like saying X is greater than or equal to 1 and Y is greater than or equal to 1. So if you look at that, that's a lot of equations, and because several of these are inequalities, there's a lot of inexact nature to these equations. And this is where, on a question like this, it's really important to remember where you are in the test, because on question 16, in theory, this is supposed to be a little bit of an easier question because you've just started the grid-ins and the difficulty level resets once you get to those grid-ins. So although question 15, that multiple choice question right before, might have been difficult, question 16 is supposed to be much easier. So let's try using that to our advantage. Everything that you see here can be used, and if you want to approach it algebraically that way, that's absolutely okay. But let's see what happens if we eliminate all of that. So let's erase this, and let's start fresh with this question and try to use to our advantage this idea that we have to have at least one of each. All right, so let's just start testing it out and see what this would look like. So let's try a value, and I always think it's easier to work with larger numbers because if you pick a value for the number of $750 bonuses, then it's likely that this smaller value would be able to divide in evenly with that. So that's just personal preference. But here, let's try something. Let's say there's only one $750 bonus. If we test it out and that doesn't work, well, then we could try two. And we could systematically test out each of those values because to get up to 3,000, there's not going to be that many. You're looking at maybe a total of 4 of these bonuses. So that's not very much testing that you would have to do. So let's try it. If we had one $750 bonus, then that means that our total amount of 3,000 minus the 750 would now be down to $2,250 worth of remaining bonuses. And if we have any number, right, just one possible number is what they're asking for, one possible number of $250 bonuses. Let's see how many $250 bonuses that would come out to. And if we divide this by 250 and do the math on that, so this is going to come out to be 2,500 would be 10 $250 bonuses. So 2,250 is going to be 9 of them. And it works. This actually goes in evenly. The math on that works out, and we can pick our correct answer choice of 9 $250 bonuses. So remember, if you're dealing with a scenario where you only have a few possibilities, then rather than coming up with an equation algebraically, you can just start at the bottom and test them out in order. So if you try 1 first for the number of $750 bonuses, if that doesn't work, try 2. If that doesn't work, try 3. And if that doesn't work, try 4. At most, you would have to just test it out 4 times, which, although it might seem repetitious, it's a lot easier than trying to come up with algebraic expressions, and in this case, many of which would be inequalities. Let's take a look at number 17. This one's a little bit more straightforward. So here, they give us an equation, and the question reads, in the equation above, a, b, and c are constants. If the equation is true for all values of x, what is the value of b? So even though this question isn't that difficult math-wise, I know that a lot of students, when first glancing at this, see this and feel a little intimidated because you have all these x's on the left and then you have the a's, b's, and c's on the right, and it looks a little bit complicated. So oftentimes, my advice on a question like this, as silly as it sounds, this is a good do something question. So even if we're not completely sure start to finish of how we would maybe solve a question, a lot of times if we just do something, anything in front of us that we could potentially simplify or express in a different way, any like terms that we could combine, whatever our math instincts are, you would be surprised at how often those are actually correct. So on a question like this, we can take a look at that left side, and a lot of students, even if they're not sure how to solve the question in its entirety, will say, oh, well, I guess I could maybe like distribute these things. And that's a great instinct. That's exactly what we should do. So let's try that. 2x times 3x would be 6x squared. 2x times positive 5 would give us a positive 10x. 3 times 3x, that's 9x. And 3 times 5, that's plus 15. And whenever we have an option to combine like terms, it's good to go ahead and simplify accordingly and do that. And so let's try that out. We get 6x squared plus 19x plus 15. So now we know that in the original question it said that this left side is equal to the right side. And if we write that in, we have equals ax squared plus bx plus c. And now a lot of times, even if we weren't sure at the beginning, it starts to become a little bit more clear that these two terms have to be equal to each other. These two terms, the 19x and the bx, have to be equal to each other. And these two terms, the 15 and the c, are equal to each other. This is really just a quadratic form of an equation, and they're really just testing our ability to recognize that this is your value for a, b, and c are these coefficients or these constants that you see on the left side that correspond with your a, b, and c that you see on the right. So if we can just recognize that similarity, and that's why I color-coded it for this, then we can hopefully say, oh, okay, well, if I'm looking for b in this equation, b is just going to be my coefficient on my x term, and so we would get b equals 19 for this. So the main takeaway on this kind of question is stick with those math instincts that you have, and even if you're not sure what's going on in an equation or a problem in its entirety from the first read, go ahead and get started. Try to do something, and a lot of times you'll be very surprised at how the clarity of what you're supposed to do comes to light after that initial step is taken. Let's take a look now at question 18. So here we see this geometric figure, and it says in the figure above, AE is parallel to CD. So that means this top line here and this bottom line, those two are parallel. And segment AD intersects CE at point B. What is the length of CE? Well, even if we were to come up with a guess on this, they're asking for the length of this segment here, CE, and they give us part of it. They already tell us that part of it is 8. So if you were to come up with a guess, you could ballpark it visually, and you could say to yourself, well, it looks a little longer than 8. I don't know, this piece compared to this piece over here, it's definitely shorter. Maybe it's about half, maybe it's a third, something like that, but you might ballpark a guess and say, I don't know, maybe that's 3 or 4 or 5 or something like that. And even relative to this side over here with the 5, you might say, well, this one looks a little bit longer than that one to me, so maybe I'd guess a little less than 5. So you could come up with a guess on this, and it is important just to recognize that in a grid-in question, just because you don't know how to find an answer exactly doesn't mean you need to give up. You'd be surprised at how easy it is to sometimes come up with a realistic guess. But in a perfect world, we don't want to come up with a guess. We want to get this exactly right. So let's see if we can figure this out. They tell us AE is parallel to CD, and if we understand parallel lines, and sometimes it's helpful to just extend those lines so that we can kind of see that relationship, that's really advantageous because it tells us that this angle in here is equal to this angle here. Those are what we would call alternate interior angles for these two parallel lines. And there's a relationship where, in terms of as a ratio in a triangle, there's a relationship between an angle and then the side opposite that angle. And that's going to tell you the ratio of the sides of a triangle, in this case, what we call similar triangles. These triangles are going to both have the same angle measures. It's just that one triangle happens to have shorter side lengths. And so this ratio here of these two opposite sides tells us the relationship of these two triangles. And hopefully we can look at that and do that math easily in our head and recognize that a 10:5 ratio reduced, that's just 2:1. Each side of this larger triangle ABE down here, this larger triangle, is going to be double the corresponding side in this smaller triangle. And once we recognize that ratio by using those alternate interior angles, then we can just say, okay, well then, let's pretend we use the other angle. So here, if we look at these angles, which are also going to be equal, then we can say, all right, well, here, if this side across from that one is 8, using that same ratio, if the bigger triangle is double the side length of the smaller one, that's enough information for us to figure out that this corresponding side is 4. And if we have the length of both of those pieces, now we can piece them together to get CE is equal to 12 once we add them up. So our correct answer on number 18 would be 12. And if you're unsure of what to do on a geometric figure question, just keep in mind that it might not be exact, but don't give up at first glance. Make sure that you still use some of those relative values to try to come up with the best possible guess. I've seen a lot of students who weren't sure about their rules for parallel lines and transversals. They weren't sure about their rules for similar triangles, but still got this question right by applying a little bit of reason and hanging in there. So that's our best advice on number 18. Up next.